Hello Internet, this is Oscar Lees again, this time with a video on using Newton's method to create fractals. If you haven't already, I would first recommend watching my video on finding the interval of convergence for Newton's method. Recall that for any differentiable function, Newton's method will converge at some points and diverge on others. As an example of Newton's method converging, if we take the arctangent as our example function and start from the point 1.25 and do several iterations of Newton's method, eventually we reach the value of 0. In fact, any real number between negative 1.4 and positive 1.4 would cause the arctangent to converge with Newton's method. But what about imaginary numbers or complex numbers, where I is the square root of negative 1, such as the point 1/2 plus I? We can't use the real number line to represent imaginary numbers, so we use the complex plane. Here, this point is represented where I meets the real part of 1/2. If we start from that point, eventually Newton's method will converge to 0. If we instead start at the point 1.1i, this will cause Newton's method to diverge. These are the points for which we tried Newton's method and it converged, and with these points we know it diverged. If we keep testing points, then everything in this shaded area would cause Newton's method to converge, and everything outside of it would cause it to diverge. This shape we call a Newton fractal. I colored it here to represent the number of iterations that it requires to converge, with light green meaning it converges quickly and darker colors meaning much slower. A Newton fractal comes from Newton's method, only now we're using the variable z instead of x to show that this number is complex, and p is any polynomial or transcendental function like the arctangent, and all we're doing is plotting its convergence behavior. Let's take a look at an explanation from Numerical Recipes in C. You may recall this book from my earlier video on Newton bisectional hybrid. About Newton fractals they write, how does this fractal emerge from something as simple as Newton's method? The answer is, local extremum causes Newton's method to shoot off to infinity. Suppose one is slightly removed from such a point, then one might be shot off not to infinity, but, by luck, right into the basin of convergence of the desired root. But that means that in the neighborhood of an extremum, there must be a tiny, perhaps distorted, copy of the basin of convergence, a kind of one bounce away copy. Similar logic shows that there can be 2 bounce copies, 3 bounce copies, and so on. A fractal thus emerges. Let's look at the canonical example of a Newton fractal, which is the function z cubed minus 1. Here the root is clearly 1. The derivative is 3z squared, and we'll plot how it converges until it reaches the root of 1, which looks like this. Let's remove the background. Now let's make several copies of this fractal. If we rotate the fractal, we get something that looks like this. We found our first root at the value of 1 plus 0i, our second at negative a half minus square root of 3 over 2i, and our third at negative a half plus square root of 3 over 2i. But we created our original fractal by having converge on the root of exactly 1. What if we changed our end condition to be stop when the absolute value of p of z is less than some epsilon, such as 10 to the minus 7? Then we can create something that looks like this. This is for the function z cubed minus 1, but Newton fractals can be created with most any function, such as the function sine of z, which converges quickly at values such as 0 and pi, but at extremum points, like pi over 2, it creates interesting fractals. Like this series of infinitely repeating disks. We can zoom in even further still, which looks like it came out of a Stanley Kubrick film. Let's look at this function, which is z to the 8th plus 15z to the 4th minus 16, which if it had a director, I'd say was Guillermo del Toro. Let's zoom in on one of these tendrils, which I think looks quite psychedelic. There is a modification that we can make to Newton's method to create a generalized Newton fractal, which is to add a variable a to multiply against our Newton step, where a is any non-zero complex number. Let's look at an example. Let's go back to our canonical example of z cubed minus 1 and multiply it by different values of a. I'm only going to use small values for a because my plotting tool had difficulty with larger ones. Here's the value 0.9, and if you recall back from my interval of convergence video, this is essentially just widening the interval to allow more of the space to converge. This is for the value of 0.8 and for the value of 0.5. But recall that we can make a any complex number, such as the value of 1/2 plus I over 4. Or even the value of 1/4 plus I over 4. You'll notice a lot more blue here, but that's because it's taking Newton's method more iterations to converge, not necessarily that less of it is convergent. Let's zoom in a little. Notice that our roots still have not changed. We're still converging on the same 3 points, and they're still represented in the Newton fractal. Let's zoom out a little. I think that looks pretty cool. Even simple functions can create complex geometry with Newton's method, and it kind of shows the importance of picking a good starting point whenever using Newton's method. There's another modification you can make which to add a variable c, another complex number. This can create a nova fractal attributed to one Paul Derbyshire, but I can't find a primary source on this. There's also a Mandelbrot variant. The code that I used, as well as the images I created, will be hosted on GitHub. Thank you for watching this mind-bending video on Newton fractals. If you have suggestions for future videos or questions or comments on this one, please be sure to leave them in the comments below. Thank you.